Hello everyone, I am Urmila, Assistant Professor at PHKD College of Engineering and Technology. Our today's topic of discussion is MSI Combinational Logic Circuits. So what we did in the last session was designing a combinational circuit using the AOI gates and then reducing it using the Boolean expression method or Cardinal method. So, in this particular session, we will move one step ahead of it, that is, we will try to implement any given combinational circuit using these two types of special devices, that is, decoders and multiplexers. Now, before going further, what we need to understand is the functioning of decoder as well as multiplexer, and then its implement and then the implementation of any combinational circuit using these two particular devices. So in this particular video, what I will cover is decoder, and in the next video section, multiplexers will be covered. So first of all, what is a decoder? So decoder is nothing but a combinational circuit which takes n number of inputs and it gives us 2 raised to n number of output lines. That is, if I have n equals to 1, then the number of input is n equals to 1 and the number of output is 2 raised to n, that is 2 raised to 2, that is 2. Fine. So this type of decoder is said to be 1 to 2 decoder. That is, it is having one input and two outputs. Now, it is always not necessary to utilize all the outputs of the decoder. There may be possibility that some of the outputs are not used. That is, they are defined as don't care combination. So, on a broader basis, we can define the decoder as a device which takes n inputs, which gives 2 raised to n outputs, of which all of them or less than 2 raised to n can be utilized. Fine. So, this is the truth table of 1 to 2 decoder. Here we are having, as explained, input n equals to 1, so output is 2 raised to n, that is 2 raised to 1, so 2. So whenever a is 0, we get d0 as 1. Whenever a is 1, we get d1 as 1. Okay, so based on this particular truth table, we can now draw a logic diagram for it. Okay, so input, and using a NOT gate, we are getting its complemented form. Fine. So the output of first AND gate, that is D0, is nothing but A bar. Okay, and D1 is nothing but A. Fine. Here, what we can do is, if we are using a 2-input gate, two of the inputs are shorted. Fine. Similarly, 2 to 4 decoder, here we have n equals to 2, so the number of outputs are 2 raised to n, that is 4. So we are having two inputs a, b, 0, 0, 0, 1, 1, 0 and 1, 1. Whenever it is 0, 0, we get output as output 1 at d0. When it is 0, 1, we get output 1 at d1, 1, 0 at d2 and 1, 1 at d2. For rest all of the cases, the output will be 0. Right. So, if we want to see the logic diagram for it, then this is nothing but D0. What is D0? We can make out from this table as it is A bar and B bar, because A and B both have 0. So we have taken two inputs, A and B, its complemented form, A bar and B bar. So D0 is nothing but A bar and B bar. D1 is A bar into B because it is 0, 1. Then D2 is A into B bar and D3 is A into B. Now let us see one of the practical example of decoder. So what we are given here is a function table and its corresponding code. What we want to do is, We want to select the function from this 4, that is add, subtract, multiply and divide. So whenever we are having code as 0, 0, I want addition to be performed. When it is 0, 1, I want subtraction to be performed. 1, 0, then multiplication, and 1, 1, then division. Then we can easily make out that this particular thing can be achieved using the decoder. This particular code can be given as input x, y, and each function makes each one of the output of my decoder. Fine. Here it is a 2-bit code, so I am using 2-bit input. So the possible outputs are 1, 2, 3 and 4 because it is 2 raised to 2, so 4. So what we are doing is designing a 2 input, 4 output combinational logic circuits in order to decode 2-bit of output. So it is simply nothing but the use of 2 to 4 decoder. Fine. So whenever it is 0, 0, I want addition. So whenever it is 0, 0, I am giving D0 as A. So if we want to represent it using a block diagram, then say this is X, this is Y, this is addition, subtraction, multiplication and division. What I am using is, what I am using is 2 to 4 decoder. Inputs are X, Y and outputs are addition, subtraction, similarly multiplication and division. Fine. Okay. So now this was a simple implementation using a decoder. Now let us understand how any combinational circuit can be implemented using decoder. For example, here I have taken a full adder. We know that full adder needs 3 inputs A, B and carry in, and it will be having 2 outputs, that is sum and carry out. So the decoder to be needed for this is 3 to 8 because there is 3 inputs and outputs are 2 raised to 3, that is 8. Fine. So we know the representation of sum in SOP form, it is 1, 2, 4, 7. So 3 inputs A, B and C, outputs are 0 to 7. So if we just simply perform the ORing of 1, 2, 4 and 7, then we get the sum. Similarly for carry, it is SOP form. Okay, there is a mistake over here. It is not 1, 2, 4. It is 3, 5 and 6. Okay, it is not 1, 2, 4, 7. It is 3, 5, 6, 7. That is a mistake over here. So what we have done over here for carry, the inputs of OR gate are D3, D5, D6 and D7. So this is how we can design any combinational circuit using the decoder. What we need to decide is, first of all, the size of the decoder, that depends on the number of inputs given, and then finally using ORing or like that gates, we can get